What if I tell you that you can apply periodic boundary condition on any 2D domain without using an ABAQUS plugin or even the tedious manual method of doing this? Do you believe me? Of course. This is exactly what I want to show in this video by introducing what I call a semi-automatic way of implementing periodic boundary condition without resorting to a software or even the onerous manual way of doing this. Let's sit back and relax as we get started with this modeling. So as we get started with this video, I want to run through some information first, some theory about the process before we actually demonstrate how the semi-automatic PBCgen generator works. So the virtual domain that we're going to be working with is basically this virtual domain that has a length of 50 by 50 microns. It's got fibers that are kind of distributed within the domain. And if we then move on from that, the material that we're going to be using is basically a reinforcement that's made of e-glass and a polypropylene material. The properties are all given here. The volume fraction of this composite is 35% and the fiber diameter is 15 micron. Now, looking more closely on this problem, the first thing we need to isolate are the corner nodes. So the corner nodes will be identified here, called the X front nodes, and a similar setup at the back ends, which are the X back nodes. It's important that you identify them because they are going to be collinear. So positionally, they will be collinear to themselves, and the kinematic linking that will give you periodic boundary condition will be imposed on these internal nodes. So the same thing we find also with the Y direction. So identify the Y top and the Y base, and again they are collinear, so they are going to be linked together. So this is the first thing we need to be aware of. Now if you move ahead with this, I will identify these corner nodes and I'll call them node 1, node 2, node 3, node 4. And because we're going to give a handle onto them because we're going to use them later on. Now, the boundary condition for this instance being a tensile test will have to appear like this. So basically what you see here is that these are the node points that are constrained to be able to impose a uniaxial tensile deformation in the X direction. So we're applying a deformation of 15 microns on this material. And so this is the setup of the problem, but clearly something has to happen with these internal nodes, and these are the nodes that we're going to impose periodic boundary condition on. So let's just look, for example, two of the nodes along the x-axis. So I've got node A and node B along the x-axis. So the kinematic linking will have to link them the way it's shown here. Now the deformation we expect basically says that the deformation of node B minus the deformation of node A. So basically, if you apply a deformation on this, the deformation of node A and minus the deformation of node B will give you a certain number. Should be equal to the deformation of node 1 and node 2. So in this case, if you're applying a deformation of 15 microns on node 2 and node 1 is fixed the way it is, so basically what it's saying is that this node 2 has to be displaced by 15 microns. And as a result, for periodicity to be applicable, we'll expect this other node B to deform as well. So what that means, basically, the deformation, this value should be equal to 15 microns, and that means this other value should also be equal to 15 microns. So this is the principle of periodic boundary condition. That's what is going to happen here. Now, we want to convert it into a canonical equation. So basically, these two need to be tied. And how do we do that? So if we rearrange the equation, move everything on the right-hand side of the equation over to the left-hand side, we have a canonical equation that basically looks like this. And so this is the equation that we're going to implement within ABAQUS for our simulation. So this is along the X direction. So let's see what happens in the Y direction. Exactly the same kind of problem. Now we have a kinematic linking in the vertical direction with node C and node D being connected. So again, whatever is going to happen to node D would mirror what's happening in node C for periodic boundary condition to be the case. So again, we've got the same equation. Node C minus node D displacement should be equal to node 4 minus node 1. Okay, so clearly node 4 will have to slide down due to Poisson effect, and so there is a deformation due to Poisson effect between node 4 and node 1, and that has to be mirrored with what's happening in node C and node D. Okay, now again there's the kinematic connection between these two. So if we rearrange the equation, get into a canonical form, we have a relationship that looks like this. So these two equations are the equations that we need to apply for all these internal nodes, both in the X and the Y direction, for us to have periodic boundary condition implemented. So let's look a little bit more on this canonical equation. So there is a function in ABAQUS called star equation that does this kinematic linking, and we're going to use that. So let's just look at what's happening here. So basically, along the X direction, so this is the X-axis. So again, this is the equation, node C minus node D minus the displacement of node 4 plus the displacement of node 1 equals 0. So along the x direction. So if we just decompose it in the way it should be, there is a coefficient of this displacement being 1, which I've highlighted as red here, node C highlighted as red, and subscript 1 being the direction of the formation. So this is the degree of freedom of what's happening on node C in the one axis of the formation, which is the x-axis, and it's got a coefficient of 1. So the same thing here, the coefficient of the second one is minus 1, the coefficient of the third one is minus 1, the coefficient of the fourth one is plus 1. I'm identifying this thing because that information will feed into the star equation function within ABAQUS that we are going to use. So if we look now, this is what the star equation. So I'm just saying, okay, constraint equation 1, which we are going to use to implement this periodic boundary condition in ABAQUS, just for node C, will look like this. So basically node C, node D, node 4, node 1. So the superscript here will appear first, which is the node number. So we would have to tag these nodes and give them a number. Now, the direction of action of those displacement, in this case being the x direction, come next with a comma. And then the third column here is the coefficient of this canonical equation. Then number 4 tells us there are 4 terms in this equation. So this is the equation that has to be written into ABAQUS in order for the periodic boundary condition to be applicable. And this equation has to all be for all the internal nodes on the system, both in the x and the y direction. So this is what happens in the x direction. So if we move again and look at the y direction with a material reference frame of 2 will appear exactly the same. The only thing that would change is this number 2, indicating that that nodal set NC is deforming in the 2 directions. So this is the equation. So this is how this will be written. So for example, again, node B and node A will have a similar behavior, node B and node A linking to node 2 and node 1, like we indicated earlier on. So now what we need to then do first is to find the input file associated with the job that we want to implement periodic boundary condition on. And so the input file will look a bit like this. So it's got the heading. Those that you understand this know already what this will look at. What we want to do is to go to the assembly section. And once we get to the assembly section, somewhere just within the end of the assembly section, we want to introduce these equations. We want to add it, update this input file with that information. However, so this is where it comes. We can do this manually all through, or we can use a code that will automatically do this for us. And then, of course, so what you could see, we'll also need to label the nodes as well. So you've got the nodes, node B and node 1. So we need to label them and find the nodal set for these things. Now, once we've done that, how do we actually do this? So there's an approach that is a manual way of implementing this. So you can actually write these star equations by hand, maybe let's say within WordPad or Notepad, and then copy them and paste into the updated input file. I've got this video which is here, which will show you how to do this manually. It's a bit tedious. It's not something that a lot of people enjoy, especially when you're trying to do a complicated model. Now, there is the automatic way, which relies on you being able to use software. So currently within the community, the ABAQUS modeling community, these are the 3 software that are available for doing this. So 2 of these first 2 are codes that I've developed myself. If you look in the description section of this video, you'll be able to find links for how you can get hold of this software. And then another researcher implemented this is the PBCGen, which again is available. You just need to Google it and find how you can get hold of the software. So these are the 3 key codes for doing this. Now, because some users may not have access to them and it can be difficult to use this code or to access them, so I decided to create this third one. Now, the third method of doing this is what I call the semi-automatic method, which is the objective of this video. And I've written a simple MATLAB function called PBCGen Semi-auto to implement this, and we're going to look into this and see what it's all about. Now, we're going to demonstrate this using 2 cases. So the first case here will be a uniaxial tension where we're applying a displacement, and then the second case will be a pure shear like I've shown here. So these are the boundary conditions that will define uniaxial tension or pure shear for the problem we're trying to solve. So what we're going to then do next is let's go into MATLAB and see the nature of the code that we're talking about. All the scripts that is generated, all the Excel scripts, all the information are available for you to download in the description section of this video. So please check them out and use them during your simulation. Okay, so let's look inside MATLAB for what we're talking about. So this is the top end of the code that we are talking about. So it's PBC2DGen semi-auto. So these are some of the preambles. So this is a bit of picture to give you an indication of what the layout of the structure, just like it's shown here. So with the X positive, X negative, Y negative, and Y positive, and the nodes identification on the edges. So the first thing we need to do is to look for the instance name within the model. So they expect that there will be one instance for your model. That's for currently what you are dealing with. So identify all the edge nodes and identify an extra edge node. I will explain this when we get into it. And then all the corner nodes, node 1, 2, 3, and 4, as identified by here, you will also notify them. And then you begin to sort out what are the X plus X negative and all that. So we explain all that. So the remainder of this is really trying to do some operation on that. So once you created the internal node, so here sorts out the internal nodes that you need. Then the next thing here is to create a file name where you will write the input, the star equations and the nodal sets. So this is what this part is doing. So you create the file name. And then within here is where you iteratively make that kinematic linking that links everything together. So if we look at here, so this is where you're writing the nodal set. So basically all the boundary nodes are being identified here. So this is what's happening in this point. And then the next thing here is where you are operating, making the kinematic linking according to the equation that we talked about. So this is what's happening here. So for the X edge in the X direction and the 2 direction, and then here is the Y edge in the X and Y direction. So you do all that and then you finish up the code. So this is the principle of what the code looks like. But what will really be interesting is for us to demonstrate this properly using a model. So to show what we are trying to do. So this is a model that I've created already in ABAQUS to implement this problem. So basically, if you look at the corner node, so we've got some edge fibers and also some inside fibers. So the material associated with this system, okay, is e-glass and polypropylene as expected. So the step analysis is a static general analysis. Okay, so that's not a problem. So the first thing we need to do is, so clearly here we've got e-glass, we've got the fiber, the matrix. Now this is a combination of those two. So what I first need to do here, apart from doing a section assignment, of the two, the first thing we need to do is to create a set. So the first set I need to create here is my corner nodes. Okay, and this basically would have to be, so I press down shift and select all the corner nodes associated with this problem. Okay, so that's the corner nodes. And then the other thing is all the edge nodes. So all edge nodes. So I could call them. So basically I press down shift and select individually all these edges. So the edges are identified and also the corner nodes are also identified. So that's really the key thing we need to do. And then once we go down here, the sections, everything is all there. So we just need to create a history output because I want to be able to do a post-processing of this. So I'm going to have corner node history output for this system. And what I would have here would be, okay, according to a set, and I'm using the corner nodes. So my reaction force in the X direction, reaction force in the Y direction, displacement in 1, displacement in 2, coordinate position 1, coordinate position 2. That is X and Y coordinate position. So this is what we're going to write into the history and we're going to use it for post-processing. So everything about this model is set up correctly as the way we would like it to be. So, okay, let's look at so there's back end is fixed. The tensile load is also applied. And then the Y base is also implemented in this model. So we've got all this implemented. So right at the base here, so you can see the the extension. So this is the job name. So I'll just make sure I know where the working directory is. So this is our current working directory. So what we're going to do is that let's go back to where PBCGen2D is existing. So I'll just copy that. Okay, and then make my current working directory that same information. So I do. So my current working direction is now that place. So all I need to do is to right click here and say write input. So once we write this input file, it becomes available for us to use right here. Okay, so now I'm going to just drag it into the system. So basically this is the input file without periodic boundary condition imposed on it. What I want to do with this is to try and improve on it so that I have periodicity implemented. So normally if you have a code, this is where you do it, where you use the software. But what we're going to do is that we're going to first, I'll just do Control F and find instance. Okay, so clearly this is the instance name for this model. So I'll Control C to copy and then go right at the top here and tell this my code, this is my instance name. So the next thing I need to do is to find all my edge nodes. So again, I'll look in, maybe do Control F or edge. Okay, so these are the edge nodes. So what I'm going to do here is I'm going to copy all of that. So currently it's looking like a matrix. So we'll copy, and then I'll just go back to this code and paste it in there. Okay, so now I'll just nudge it so that it looks okay. So we are lucky with this particular instance that the matrix looks normal. So if we go back here and look at what we have here, so it's a square matrix, it looks fine. There may be instances where you will not have a square matrix. You may have something that looks like this. So the main square matrix and then some kind of trailing element extra added to it. So this could be what we will see. Remember, it's the nodal set that we are using. So we're using this, not the element set. So where you have this extra, that is a trailing to your system. This is why I've provided this particular all nodes extra for where you have a trailing system. Because if you try to combine all that within this simple instance, it would not work. So this is why I've provided this trailing edge, this extra, so that in the end, when you combine them, you now have a complete system. So this is that. So what we are going to, so we've provided this information. Now there is nothing on the extra, so I'm going to leave it as open. That's fine. Now we need to identify what these nodal numbers, nodal sets are. Okay, so what we are going to do is we'll go back to our model, and then let's say in the assembly option, you open the assembly option under your mesh, you show the mesh levels, and then you go there. So this is fine. So what we are going to, what we see here is that at this corner, this is 14. At the other end, this is 3, this is 6, and this is 10. So 14, 3, 6, and 10. So number 1 is 14, this is 6, this is 3, and this is 10. So if you're doing this automatically, the software will work out all this information and make this allocation for yourself. Of course, we're not using the software, we're using kind of a middle house, which is the semi-automatic. So you've got to provide this information, and then the software will then update itself and provide all the other extra things that you need. So the same thing will apply here. So let's look at the X positive. So the X positive will be the face in front here. Okay, so the face in front. So let's look at, so it starts with 3 and then it goes. So we need to arrange it exactly as it is here. Exactly from the bottom to the top as you go up. So we got 3, 37, 38. So I would write here 3. No. So 3, 37. So if you look here, 37, 38, it keeps increasing just until, so let me switch this over to maybe assembly module. So let's switch this to material. So you see it starts from 37 up to 53, somewhere around here, and then it jumps to 4. So I'm going to do 37.1.53. So I'm using ABAQUS Speak to just do a stepwise. I'm using a MATLAB Speak to do a stepwise formation of the numbers. So from 37 to 53, and then I'll jump to 4, space 4, and then after 4, so the next thing we have here will be 225 to 230, again incremental. So I'll do 225, 1, 230, incremental, and then we'll now look at 5. And after 5, the last two numbers are 71, 72, and 6. So 71, 72, and 6. So basically here we've provided all the coordinate position for X. So we provided everything for the X, beginning from 3. So this, if I just copy that and you paste it here, so you could see it basically gives you the numbers from 37 to 53. If you know how MATLAB works, then this will be nothing for you. So let's look at the negative side. So I'm going to move to the negative, which is the back end. So we'll do the same. So we start with 14, 130, but it's reducing 129, 128. So first I'll do 14, 130 minus 1, and then until we get to 114. 114. Okay, so I'll get to 114, and then we get 13, and then 236 to 231. So 236 minus 1, 231, and then 11. So we get 11, 105, is it 107, 106, and then 10 in the end. So 106, 107, 10 in the end. So 107, 106. So again, this is what happens in the negative side. So the positive y direction will be right at the top end here. So we're going to start with 10. Now it starts from 105 and goes to 97 in a decreasing format. So 105 minus 197, and then we'll jump to 9, and then 225 to 218. So 225 minus 1 to 218, and then it goes to 7, and then after that you get 81 to 73. So 81 minus 1 to 73, and then 6 at the end. So this is what's happening at the top end. So we then move ahead and then look at what's happening at the bottom end. So this is the only kind of this is why it's semi, because you're having to do this yourself rather than depending on the software to impose this. So it's kind of a halfway house. It does work. So let's start with 14. Now the next thing here is 131 up to 139. So it's incremental now. 131, 1 and 139. Okay. And then it just goes to 1, and then 237, 1, 237 up to 243, 243. And then after that, you get number 2, and then it goes to 28 up onto 36, 1, 36. And then the last number there is 3. So basically what we have here is an x positive, x negative for the edges. Okay, so don't worry about, just list them out exactly the way they should be for the edges. And then now the code will go in and try and do post-processing to isolate which ones are the internal nodes, which is what's happening here, and then it runs through to the end. So we've specified the information that we need. Okay, so what we then need to now do is just to run the code. So if we run the code, then it runs perfectly and we get the result here. So remember, we still have this one open here. So what I'm going to do here is going to save it as, so I'm just going to attach at the end of it updated. Okay, and you have to add IMP for it because this is a file name for ABAQUS. So we've got that there. Now the ones that we wrote, so you can see what this file looks like. So it's got all the information that we have there. So I'm just going to Ctrl+C to copy every one of it and then go back here. So what we want is that we navigate in our main code, updated code, to the part where you got the end of the assembly. Okay, so we'll just move and find where the end of the assembly is. Remember, we'll copy, Ctrl+C to copy this, then go to the code, end of the assembly, and then add that information. Okay, so you've added it. So what has happened here is that if you look more closely, you see that we've updated with all the star equations this file. Okay, and everything is fine here, and we know this is the position where this information is. So all we then need to do is just to go to ABAQUS now and run this model. So if we go into ABAQUS here, I will have to import that model again with the updated input file. So I'll put the information, switch this to input file. So this is the updated input file, the way it should be. So maybe while I'm at this, I could turn off the meshes. Okay, so the updated input file has been retrieved and it's coming here. So you could see the constraint equations are all there as expected. So this has been automatically written from the code in the way we want it. So everything here is fine, and our boundary conditions are all fine. All we need to then do is to set up the job to run. So let's say maybe extension. So let's just do an extension simulation, and then we'll submit this to run. So while the job is running, what I want to do, because we also want to do a shear case, so I'm going to create a copy of this model and then just switch it to maybe pure Shear XY. Okay, so we're not going to worry about that because already we know that in this shear case there's already periodicity implemented because we are borrowing what we used before. So the only place we need to make the changes is to go to this case. So if we look at this basically is the loading that we applied. So what we need to do for this state case is I'm going to make this load to be in the y direction, because we know that this is what the boundary condition will look like. These two, I'm going to sort of suppress them, and then I introduce a load at the top end here, which is the shear in the yx plane. So that will happen at the top, and So it will be acting in the one direction with the same load of 15. So we've got a shear acting there and shear acting there. The last thing we just need to fix fixed node 1. Okay, because this is what boundary condition we expect to use. So we select that and fix it, node 1 and node 2. So this is sort of what we have. So this point is fixed, this point will experience shear, and everything in between will be experiencing periodic boundary condition. So, and then we can then go back here and then do pure X, shear XY. So we'll set the job to run, and then we'll submit that as well to run. Okay, so we'll look at the tensile case. So basically, this is a result you generate from the tensile case. It shows you the normal expected periodic boundary condition, especially when you look at the PE direction, the plastic strain. So you get the deformation of what's happening here. So there's a clear fracture or plastic deformation around this region. So this is what you get with that. So if we look at the shear case as well, so you get again some interesting result like this, which is pure shear as expected. So if you look at the plastic strain, you can see there's a clear shear band right in the middle there. Everything about the simulation looks all right, and this is a periodic boundary condition that we expected. The next thing that we need to then do here is to try and see if we can generate the stress strain data from this. So let's look at the tensile case. And then, so what do we do with the tensile case? So you just use this button, and we're operating on the history output, and then press down shift control, and then scroll down, still pressing down control. So we select all those variables that we asked, the coordinate system, the reaction force, and displacement, and then we just plot it. So obviously that information gets plotted this way, so don't worry about it. We're just going to use our tools, Excel utilities, to export this into an Excel file, because with the Excel file we can then do some manipulation. I've already prepared an Excel script which you will need to work with this. So this is the Excel file that we generate. So I'm going to say Control A and Control C to select all of that. And then the Excel file that I talked about that I prepared basically looks like this. So the uniaxial case, I'll just paste that information here. It basically generates stress strain data for the first case. If you look right here, the length, the width, and the height are all given. So it was a 50-50 micron system because it's a 2D problem. The depth I choose as 1. And then it calculates the Young's modulus and the effective strength of this material. So if you look here, it will tell you how that information came about. So we'll do the same for the shear. So if we go back and get the shear, so we go here. So the shear case will be this instance. So we'll do a similar thing with the shear. So again, operate on the history output, select all that, and then select the remaining case here and plot that information. So again, we get that result. All we need to do is to do Excel utilities, extract it as usual, and that will give us an Excel file which we are going to use. So for the shear case, it's our Excel file. So Control A to select or Control C to copy, and then we'll go back into this code and paste it. So we get our results as they should be, and the Young's modulus calculated, the effective strength is calculated. So if we put everything together, so we get the result the way it should be here. So basically you get the Young's modulus in the XX direction, the transverse modulus, the shear modulus, and the strength and the stiffness and the straight. So this is for a very small element. So what I've tried to show here is how you can actually use this semi-automatic method to generate your stress strain plot by implementing periodic boundary condition in the domain. If you're interested in how to do this automatically using a code without having to go into all these kind of details, then this is the video that I've made that will help you. If you want to learn a little bit more about the theory of periodic boundary condition in more depth, then this is another video that can help you. Thank you for your interest in this channel. I'll see you in the next video. Bye bye.